So we will continue with the remaining part of relational algebra. One important operation is division operation. Say we have a relation R Z. So this is the schema. And so there is another, that is say S Y. So Y is that set of attributes forming the schema. And Y is a subset of Z. But if I put this one as X, so X is a subset of Z. And Y equals to Z minus X. If we write Rz or simply R divided by Sx, say it gives any relational operator, relational algebra operation that results into another relation. Suppose we are getting the relation T, and that will have the schema Y. That is a part of the attributes which is not present, part of the attributes in R which is not present in S. Y equals to Z minus X. So basically, from here we'll get values of Y which is present for every value of X. Every value of X. Or more formally, we can say Ty, that is the final outcome, includes a tuple T if say Tr appears in this relation and it must satisfy the following condition. That is, for every tuple T here, if Tr appears in this relation such that Tr Y equals to T. That is the first one. See, T, it is having the schema Y. Here, the schema is Z equals to nothing but X union Y. So, this part says that we'll have a tuple here. We'll have a tuple T here, such that here there is a tuple with T, and not only that, and with Trx equals to Ts. So we are considering a tuple here, say Ts. Here we are talking about Tr. For every tuple of Ts in Sx. As we said, these are the two conditions. That means, if we repeat it again, we can have a triple T here. If it is so, then that value of y must be present in A, that is in here. So TRY equals to T. Corresponding, so it will have, say, must exist as these y value of a triple T are here. And not only that, for every combination of TS in S, for every combination of TS in S, TRX, if I take the projection of X union Y. So basically, from here, if we take a triple T, it means that it is present means we have some triple TRY equals to T and TRX equals to TS. This one for every TS belonging to S. If we take a concrete example, then it will be easier to understand the meaning. Say, if we go for say integer division, say 10 divided by 4, what will we get? As if 4 as a whole, how many times it appears here? Twice. Same thing. For some value of x, for some value of y, how many times this thing appears as a whole? So if I consider, say, R is nothing but the result, it is having role, subject code, and score. The students who have appeared in some subjects in the exam, this is the primary key. And we have the score. If somebody is not appearing, we don't have the score. We don't have any entry, let us say. No entry for absent candidates. Now, say, we have the subject list. Say S stands for the subject. Put subject code, say subject name, etc. So basically we have considered a subject, list of the subject, subject code, subject name, etc. And the result of the students, role, subject code, this is the primary key, and score. Those who are absent, we don't have any entry. Suppose we want to find roll number of the students who did not miss any exam. That means we want to find out the roll number who have the entry for each and every subject, for all subjects. So we can think about the division operation. Now, if I consider, say this is R, then this is the Z, the set of attributes. We cannot write like this, that result divided by subject, because as if we try to remember, if the set of attributes Z is here, if it is say Y, say this is X, so X must be a subset of Z. That is not true. If I consider this is X, this is Z, it is not subset, but see, I need only the S code. So we can take the projection. So instead of doing this, so if we go for say result, and again in the outcome, what I need, the roll number. The output schema will be, okay, let us go step by step. So if I consider pi escort subject, so here I am having a schema with subject code only. Then if I keep here result, what will happen? The output schema will be z minus x, y. So output schema will be roll escort score minus escort. So we'll be getting only roll score. Then there is a problem. We cannot have roll score same for all the subjects. I will be scoring the same for all the subjects, so that will create problem. So as we are interested in knowing the students, so we will be writing roll score. That's all. So now it will give us for which combination, what are the roll numbers for roll numbers corresponding to that every subject entry is present here. Right? Now see, these we can have, this is a derived operation. So this can be expressed in terms of the fundamental operation. As we considered initial that R divided by Sx and the result is giving us Ty. X is a subset of Z, Y equals to Z minus X. So what we can do, if I consider this one, from R, we are taking the projection of Y. So all values of Y that we are taking. Now if we go for T1 into S, then we will be getting the all possible combination of Y and X. So from here we have taken Y. Now next step, when we are doing this Cartesian product, we are getting the all possible combination of xy values. Now from these, if we subtract R, what is the schema? Here the schema is nothing but xy, z equals to x union y. That means which xy combinations are present. So it has given us all y. It has given us all combination of xy. It is giving xy combination present. So if we go for subtraction, this whole thing gives xy combinations not in R. Now if we take the projection of y from here, then basically in T2 what we are getting, y value for which xy combination not in R. So these are the set of y values which must not appear after the division operation. So the outcome is T will be, so I am using the assignment operator. This is the all possible y. These are the y values for which all xy combinations are not present. So T1 minus T2, that is the outcome of our division operation. So see, we can express the division operation as a set of our fundamental operation. Now if we again map this to this particular example, say first of all, I don't need every information of result, so I am taking these are the additional things for this particular case, as I will be requiring only pi roll escort. sorry, from result, say this is my, say R, and putting this into R. So basically R is having roll and escort from the result, as I don't require the score. Then from subject, I need only subject code. Say S. Now with these, I want to carry out the division. If I follow this one, what is our Y? X is S code, Z equals to X union Y equals to roll S code. So Y is nothing but Y is roll. So if I put it this way now, so I am taking the roll of the students. So this is the all roll numbers who have appeared in at least one example. So I am taking, so as if this is my current all possible roll numbers. I don't know whether I have the score for everybody or not. Then if we go for say T1 cross S, so all possible roll subject code combination we are getting. From here we are subtracting R. This is giving me the roll S code combinations which are present. This is all possible roll subject code combination. So among those which are present, I am removing those. That means this expression gives which roll subject combinations are not present. From such combination, I am taking the roll numbers. So these are the roll numbers. For them, all possible combinations with subject is not present. And these are the total set of roll numbers. So finally, if we do this, so these will give us roll numbers for whom all roll S1 combination is combination exists. So that is the division operation. Right? We will go for aggregate function and grouping. Okay, suppose we have a result, roll, subject code, sys code for all the students in all the subjects. See, if we have a student kind of thing, say roll, name, others. Say we may have some functions, say in the commercial languages, say I want to display the name in uppercase. If I go for this will show me the names, but those may not be in uppercase. So basically, there is some, say, let us assume there is a function upper. So if I think about this upper name, now it will be shown into uppercase. Now how does it work? Say in student relation, say these are the tuples. So it takes a tuple, then it will go for a projection. So there is some name. Upper is applied on this, and that comes into the outcome. It goes for the next tuple. Again, the name is say X, Y, Z. Again, it will take the projection. It finds that there is a function that will be converted. So this will go on. That means this is an example that acts on individual people and generates an output for each tuple. Right? So these are basically non-aggregate functions kind of thing. Non-aggregate function that acts on individual tuple, and for every tuple it will give us some result. So when we talk about aggregate, so obviously it acts on a collection and returns a single value for the collection. It is shown this way, scripted F. Here I can put an aggregate function, say average. Average of what? So the function, aggregate function, the expression on which it will, expression will be consisting of some attribute, say average score. Result. So we want to find out the average score. So as if the output schema is like this, as if. Now what is the collection? Collection is all the tuples. Collection is all the tuples. So we will be getting only one row for the whole collection. So in output schema, one row or one tuple or collection. As of now, the collection is consisting of all the tuples in the row. All the tuples in the row. So average score, what is the average score? That will be shown. We can go on putting multiple functions, multiple aggregate functions. Say standard deviation of score. So now the schema will have standard deviation score. Or I can go for renaming the outcome, or I can assign the result, say to T as average standard deviation. So in the outcome, it will be named as this. And if I want to develop an expression in the subsequent steps, I can work with T with these are the attributes. Now somebody may say that, okay, what is the meaning that I will be taking the average of all the students and all the subjects? That may not be so meaningful. So if I want to find out the average score and standard deviation for a particular subject, so obviously then I can apply some refinement here. Say for subject code equals to S1 result. On this, I will carry out this operation. So this one will be done. This will be giving us some relation to filtering. So on that it will work. Now suppose I want to have the subject code average score for all the subjects S1, S2, S3, etc. etc. Now what you can do, here comes the importance of this grouping. So far it was considering that all the tuples in my relation, they form the single collection. Now we can go for a grouping. Here we can specify the grouping expression. Say score. Average score. Result. So now what you can do, it understands that the tuples are to be grouped based on the subject code. So all the tuples of S1 will form a group, all the tuples of S2 will form a group, S3 will form a like that. Now this aggregate function will act on this grouping, act on the individual group. For every group, it will now give us some output. So now the schema will be S score, average score. S1, S2, S3 for every group will be getting some result. So whenever we are using aggregate function and grouping, the output schema will be the grouping attributes and aggregate functions. Now see, whenever we are going for this aggregate function and grouping, so basically these things and these things, they will appear in the schema. And we can put them as per our convenient naming by assigning it to a relation with proper naming of the attributes. Now one thing we must remember, we cannot have any other non-aggregate kind of expression. Say, if somebody considers you can be writing name, say role. For every group, role can have multiple values, not a single value. So we cannot put anything, a simple attribute or any other kind of expression which is non-aggregate. Mind it, because I'm mentioning this, it will have a direct implementation kind of thing in SQL also. That means, see here, what information we are getting for every group a single value. For every group, what can have a single value? Either the aggregate functions or the grouping expression. It is ensured, as we have done the grouping based on score, for every group there will be a single value of score. I cannot put anything else. So, whenever we are dealing with the aggregate function and grouping, the output schema can have only the grouping attributes and the aggregate functions. Now, the grouping may be on multiple attributes. Suppose in the result, so we have role in which department the students belongs, score and score. Say these score may exist for multiple departments. Say your common maths, it's across same code across multiple departments. Say if I want to find that department wise, subject code wise, highest code. See, we can have this kind of sum and aggregate function, sum of the particular values, average. Now see, whenever we are going for this, computing this statistical information, now values are ignored. Suppose there is a score 70, 80, and for another student say this is not known, if it is null. So if I consider these three only, say we will consider sum is 150, somebody may say that this is 0. If I go for averaging, it will ignore this one, 70 plus 80 by 2. It's not 70 plus 80 plus 0 by 3. This will be ignored. So anyway, we can have max, mean, count, number of elements like that. Now, so department wise, subject code wise, that means see, department D1, subject code 1, department D1, subject code 2, if I consider 3 subjects and 2 departments, department D2, subject code 1, D2, subject code 2, D2, subject code 3, like this. That means we will have to group them based on the departments. Within the departments, we will have to further group them according to the subject code. Right? So for this one, the grouping attribute will be, the grouping is on department code and subject code. That is, they are to be grouped based on the department. Within the department, those will be grouped according to the subject. Now we want to find out maximum score. Right? Similarly, if we want to have minimum score, average score, we can go on putting those things, mean score, etc., etc. So we can have the aggregate function. Output schema will be grouping attributes, union, aggregate functions used. Say, if instead of this one, if I write S code, subject B code, we'll be getting the same set of information. Maybe that, as if physically how we are interpreting, they will be grouped based on the subject first, then within the subject based on the department. So ultimately we'll be getting S1 D1, S1 D2 C, S2 D1, S2 D2, S3 D1, S3 D3. Same information we will be getting. So these ordering at the time of writing the function, writing this expression doesn't matter. We'll be getting, then that their appearance in the outcome that may change, but essentially we'll be getting the same information. So that's all for the relational algebra. Now we'll look into relational calculus. There are two types. Basically, we will consider tuple relational calculus. Now, we are having relational algebra. We are having relational calculus. If we compare them, see, this is the premise of comparison. Then this is procedural. This is non-procedural. Because both are seen given by the relational model to specify the requirement or how to do the things. So, how to interact with the database, how to specify my requirement. In this case, already we have seen, as we have specified set of operations. So, we are specifying how to get the data, not only what. Here we see that we specify what data is required. not how. Suppose we have, say, relations like these: subject code, subject name, say full marks, or say subject type, subtype, say this is theory or sessional, like that, etc. We have the student, role name, and other information for all the students, all the subjects, all the students. Then say result for every student, every subject. This is the primary key, we have the student. Suppose find the name of all students. So the expression will be of this form. The T, this is our tuple variable. So tuple variable that can hold a tuple from its range relation. Here we are specifying that T belongs to student. Right? So this is the range relation for the tuple variable T, which is appearing on the left hand side of the bar. So set of T tuple variables, T is satisfying these. So range relation, that means the tuple variable ranges over this relation. So it can take any tuple from that. So basically it will give us a set of tuples from here. We are yet to get the name. So this is just simply like selection of our student. So it specifies what it is not talking about any operation. It says that I need set of tuple variables T such that T belongs to student. That's all. Whether it will be select operation or something else, those are not being mentioned. Now suppose in our student relation, suppose, okay, if I want to get the name, the one that we started, we can specify T dot name as if T even think that a structure kind of thing. So from T I want to have the name. T is holding the people of a student. Somebody can write it this way also, T name. That will also. Now suppose find the name of all students. Say living in the city Kolkata. Suppose in our student relation, along with role and etc., we have a city, that kind of thing also. So then we can specify that T belongs to student and T dot city equals to Kolkata. So this is a tuple variable, ranges of a student. From a student tuple, it will check whether if it is city equals to Calcutta, then it will give nursery. So that will be specifying the requirement. Now suppose, say we have also, say in our student schema, if I consider we have role, name, city, and the department code, and we also have a department schema with department code and department name. Say for every student, show name of the student and name and corresponding department name. Now see, our requirement is to have these things of corresponding department, name of the corresponding department. So now I cannot have only a tuple, single tuple variable. Say S is a tuple variable for students, say T is a tuple variable for department. So from S, I want to find out the name. From D, we want to find out department name such that student S, either one can write this way also, or one can write S belongs to student. And department D and correspondence S dot D code equals to D dot D. It's not that we are talking about condition product and all those things. What about operation we don't know. This is my requirement. Tables from S and student and department, if it is same, then show me the name and the name of the student, name of the department. Now I am making a little bit of change here. Show the name of the students studying in department named as XYZ. So see, basically from the student tuple, I want to get the name given the range relation for S is student. Now, if, see, I don't have the department name in this student tuple, so I have to find that whether it matches with the department code of department named XYZ. So how shall we do that? Sometimes we feel that, okay, that procedural means that is much more complex. We have to specify the steps, how can we do the operation, the procedure, etc., etc. But see, already we are tuned in the thought process of procedural fashion. Now we'll get the feel of the difficulty in non-procedural specification. The tuple variable that appears on the left hand side of bar, these are the free variables. We may have to introduce additional tuple variable on the right side of var. These are free and unbounded. These are bounded. Such things are the bounded tuple variable. And not always associated with binding quantifier. Now this binding quantifier maybe say if x is a tuple variable, but this is existential quantifier. That is, there exists an x. There exists x. This is the universal quantifier. That is for all x. It is much more difficult. We will come for this later. So if we think about this one now, in this case, say we have taken a tuple from student. From this tuple, we will take this name provided there exists an x where x belongs to department and this may correspond x dot decode equals to s dot decode and x dot dename equals to xyz. So we have taken a student tuple. It will appear in the outcome provided there exists an x. X is a department tuple. Department code of this tuple x and the student tuple s are same, and this is in department B. Right? So that is the existential quantifier. Now, this universal quantifier, this is difficult, little bit. So let us take an example. Suppose if I want to find out, say, from a result okay, find roll number of students who have scored greater than equals to 50 in all subjects. So in student we have the roll numbers. So okay. So I am considering for the student, say ST is the tuple value. So I want to find out ST dot row such that ST ranges over student Now see, when we say for all x, this is the range relation is universal relation. Universal relation is the superset of every relation. It's not only our student, subject, and those things we have specified. Conceptually, this is universal. So for anything in this universal relation, it must be true. Here, if it is true for at least in one tuple, then it is good enough. It will be given true. But if I write for all x, then some predicate, then it must be true. Say if I put it here, and etc. etc. So if this portion holds, this portion will be giving us true if any tuple from the universal relation satisfies this condition. So this is very critical. We'll have to go in a different manner. Say, what is our situation now? That this student will come in the outcome if in say this, if I assume in my mind that for every subject in subject relation, some condition has to be satisfied. When you say for every, so I consider for all. But see, this is universal. This SU is not of only subject, it may be anything. But I am obviously, the thing is that I am interested only if it satisfies for every tuple in the subject. Then forcibly for others, I have to make this true. So if I write not subject SU, so that means for non-subject tuples from the universal relation, this question is making it true. If SU is holding a subject tuple, then this portion is false. Then only the OR part will be checked. So this portion will be checked for whom? Only for subject tuples. Right? Only for subject tuples. Is it clear? This is very important concept. When we are using this for all kind of thing, it ranges over universal relation. Now, in my mind, I am interested only when it is following the subject tuples. But for others also, I have to make this true. So we have put not subject SU. So for any tuple other than the subject tuple on which I am not interested, I am making this forcibly true. It will look into if it is a OR, condition 1 or condition 2. If this is true, then it will never look into this condition. That is the beauty of OR. If it is false, then it will come here. So when it will become false, it will become false only if it is coming from the subject. Then for the subject tuples, it will come here. Now for subject tuples, what I need to find? That in this particular subject, the student must have got greater than or equals to 50. From where I find the score? From the result table. So say R is the say table for result relation. If I consider say RE, so there exists an RE result RE and this RE dot roll equals to ST dot roll and RE dot subject code equals to SU dot subject code and RE dot score greater than equals to 50. So this one is closed, this one is closed. Finally, that closing bracket, curly braces. See, curly braces, because we are talking about the set of tables. So now see, from the student, a roll will appear. Then the requirement is that for every subject it must have score greater than or equal to 50. So we are considering universal quantifier, but it ranges over the universal relation. So for non-subject code, forcibly it is made true. But if it is a subject table, if it is taking from subject relation, then only it will come here. Then it will look for a result entry such that these result entry and this subject code they are same, and the roll number of the student and the result entry is same, and the score is greater than or equal to 50. So right, so that is the universal quantifier. We are still left with some part of relational algebra, relational calculus. So we continue from here in the next step. By the universal quantifier, whenever we are using, we will have to be very careful and we have to understand. So all the time, non-procedural is better. At least at this point of time, I find that always it is not so.